Good afternoon and welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor. Today we're going to be looking at data-driven materials innovation where machine learning meets physics. We're going to find out how you can speed up materials innovation, save time, save cost, by leveraging a combination of physics-based simulations and chemistry-informed machine learning. Now we have a sponsor for today's webinar. They've supplied not only the fascinating topic, but also our fantastic guest. They're a long-time Chemistry World partner that we're always delighted to work with, and that's Schrödinger. Schrödinger are transforming the way that therapeutics and materials are discovered and developed by pioneering a physics-based software platform that enables discovery of high-quality novel molecules for drug development and materials applications more rapidly and at lower cost compared to the old school bucket chemistry way of doing it. The software platform is used by biopharmaceutical and industrial companies, by academics, and by government labs around the world. So thank you to Schrödinger for hooking us up with such an excellent guest and for supplying such an interesting topic to talk about that I know will be relevant to a great deal of you who are watching here today. Thank you, all of you, for joining us. Before I tell you a bit more about what we'll be learning today, I'd just like to introduce you to the platform. We use something called GoToWebinar. I'm sure you'll be familiar with all of these sorts of online webinar streaming type services, but GoToWebinar, of course, has its own quirks. Now, depending on what platform you have joined us from, be that Mac or a Windows PC or phone or even a tablet, then the things may move around slightly, but you should find somewhere on the page that there is a questions box or a chat box, might be labeled ask the presenter a question, or might just say chat. That box is your best way to get in touch with us throughout the course of this presentation. And you joining us and the questions that you ask really are the lifeblood of every Chemistry World webinar. So please, if you have any questions at any point throughout the presentation, drop them into that questions box and we will do our utmost best to answer them. We've got a good chunk, about 15 minutes or so of questions after the presentation, so we will do our best to get through as many of your questions as we possibly can. I can see already that Levin has managed to drop in a question in there, so clearly it's working for all of you out there. So do please keep them coming as we go through the presentation, and we'll put them to our guest speaker at the end. So what are we going to be learning about today? Well, we're going to be seeing how Schrödinger's tools can help to overcome common challenges by using a combination of physics-based simulation data, enterprise informatics, and chemistry-informed machine learning. If you're not sure what that is, you will be learning very shortly. We're going to see a few different case studies that highlight how machine learning models can improve viscosity predictions, for example, or predict the ionic conductivity in lithium-ion battery electrolytes. Just two examples of how this approach can really help us better understand the systems that we're developing and therefore save time and money. So we're going to see how to leverage the synergy power of machine learning and simulations to drive materials innovation. We'll look at some practical case studies from across different industries, and we're going to have a look at the key areas in your own research and development where machine learning and simulation might be able to provide value. And doing all of that for us in the next hour is Anand Chandra. Anand joined Schrödinger in 2019, currently product manager of MS Informatics, has a PhD in materials science, and before that worked on a number of different topics with polymer informatics, machine learning, force fields, and machine learning for electronic structure calculations. So he has machine learning right through his academic history so far, and is definitely the right person to bring us up to date on not only what this is, but also what it can do for you in your lab, in your industry, in your research, in your interests. So that is, I think, enough from me. Do keep your questions coming in as we go throughout the webinar. Very much look forward to putting them to Anand later on. For the next person we'll hit, let's get Anand up on screen and check that we can hear you and see you, Anand. Anand, thank you for joining us. I will hand over to you now and come back later on with some audience questions.
Thank you so much, Ben, and thank you very much for the kind introduction. So today I'm going to be talking about data-driven materials innovation, where machine learning meets physics. And so I think the title speaks for itself. We all know how powerful machine learning has been the past few decades, and even the past few years, past 1 year or so with ChatGPT. It's really, it's really at the forefront of everyone's interest right now. But within Schrödinger, we have been using machine learning for quite a long time. And we've been able to combine it with our computational material science and drug discovery platform, physics-based platform, and also our enterprise solution for data management and collaborative ideation called LiveDesign. So in Schrödinger, I mean, as the title suggests, the goal is to come up with better solutions to enable creation of new chemistry and new formulations and new materials. And using a combination of machine learning methods and computational material science methods, quantum mechanics and molecular dynamics, and also enterprise informatics methods where you can really bring together experimentalists and machine learning and data analysts and physicists and chemists in one single platform to come up with new chemistry. This combined power is what is the best solution that Schrödinger offers. And throughout this presentation, I'll be giving out case studies about how our solutions can affect different verticals in material science with a combination of physics-based and machine learning approaches. But the focus is going to be on machine learning for this presentation. And the basic approach of machine learning, at least supervised learning in material science, is that we want to predict properties of materials, molecules, 3D structures, and formulations without going through the computational, without going to either the physics-based route or experimental route. An actual synthesis and characterization of a new material can take of the order of a few months, and doing a DFT calculation on a large molecule or on a big or doing an MD simulation on a huge 500,000 atomic system can take of the order of hours or a few days. But with machine learning, what we can do is we can select the right featurization technique for different types of materials and combine it with the right machine learning algorithm and come up with predictions of the order of a few seconds. So the key part of machine learning for material science is the featurization part. Depending on what material we have, whether it's a small molecule or a polymer or a 3D crystal, periodic inorganic solid, or a formulation or mixture, we really need to be careful about which featurization technique that we select. Not all techniques work for all classes of material. For example, for small molecules, we know that 2D descriptors are very well established in the drug discovery and chemistry communities, and they usually perform quite well for many material science properties. But in addition to that, we also have graph-based convolutional neural networks, which don't require any explicit descriptors or fingerprints, but the featurization happens within the graph convolutional operation itself. And these perform really well for large data sets. They outperform the 2D descriptors and fingerprints. And similarly for polymers, if you treat a polymer as simply as a molecule, you're losing out on all the chemistry and physics that make a large molecular weight polymer unique. So we've come up with some customized descriptors to take into account the polymer chemistry and polymer physics and how this translates into the properties of a polymer property, like glass transition temperature. Finally, for 3D solids, for inorganic solids, the defects, the 3D structure, the defect energies, and these things are really dependent on the atomic sites and the atomic environments. And we have a whole host of 3D featurization techniques that can actually perform machine learning on these type of materials. And I'll be showing case studies on this as well. And finally, for most applications in chemical R&D, for example, in consumer packaged goods, fragrances and flavors, or even for battery electrolytes, most people are actually looking into mixtures of molecules rather than a single component, or they could be looking into a mixture of a polymer and an additive, for example. And again, in this case, we need to have a customized featurization approach for these mixtures. And on the right side, for all these different materials, for small molecules, polymers, with the help of Schrödinger's physics-based platform, we can actually obtain descriptors using quantum mechanics and molecular dynamics, for example. And these really improve the accuracy of our machine learning models. And this is what I'm going to be showcasing in some of the scientific case studies in this presentation. So before I go into our case studies, I wanted to give a brief overview of the machine learning tools that are available within Schrödinger and how they are very commonly used. The most commonly used tool for machine learning within Schrödinger is AutoQSAR. So AutoQSAR is a fully automated machine learning solution to do machine learning for molecules. And here, what you would do is just provide a CSV file with a bunch of molecules in one column, like a smile string notation, and another column with the property of the molecule, for example, your viscosity or your density or your toxicity, for example, and you would load this into Maestro, which is our desktop solution, and you would open up the AutoQSAR panel and just click train a model, and it would automatically do the data splitting into train test splits, and it would select the most informative descriptors, and depending on whether you want to do regression or classification, it would try out different machine learning algorithms and automatically select the best performing model for that particular data set that you've provided. So one quick example of this is showing how, for example, I downloaded this data set of 392 ionic liquids. So ionic liquids are liquids that are very important for the energy industry, for battery materials. And the goal here is to come up with ionic liquids that improve the electrical conductivity of these batteries. And on the left side, you can see a histogram distribution of the electrical conductivity of these ionic liquids. So here, the molecule is represented as a combined smile string. So you would have the positively charged ion and the negatively charged ion essentially separated by a dot. And you can automatically load this into Maestro just by providing the CSV file and train a bunch of different machine learning models. And it would do fingerprint-based models as well as descriptor-based models. So the fingerprint-based models are more based on the substructure of the molecule. Descriptor-based models are based on fixed numeric quantities, things like your number of aromatic chains, aromatic bonds, your number of rotatable bonds, and the number of sp3 carbons, and your total polar surface area, for example. These are the type of descriptors that AutoQSAR trains on. So AutoQSAR trains both fingerprint-based models and descriptor-based models. So in the case where the best performing model is a fingerprint-based model, we can actually visualize which parts of the molecule are contributing to the increase in the electrical conductivity and which parts of the molecule are contributing to a decrease in the electrical conductivity. So you can see here the fluoride groups are highlighted in red. So these parts of the molecule are actually contributing to an increase in the electrical conductivity, whereas the blue parts of the molecule shown here are actually contributing to a decrease in the electrical conductivity. So this is a very useful information for chemists to actually design, to direct the chemistry towards an area where we're actually interested in, towards a property space that we're trying to optimize. So once you've trained a model, you can either select the best performing model or a top 10 performing model together to make a consensus prediction to get both the prediction as well as the uncertainty. Similarly, we also have a new tool called DeepAutoQSAR. So DeepAutoQSAR is based on more modern approaches like graph convolutional approaches, transformer-based approaches, and also tree-based approaches like random forest, XGBoost, for example. And DeepAutoQSAR works works very well when you have more than 500 or 1,000 data points. If you have anything less than 500 data points, we would suggest to use AutoQSAR. If you have more than 500 data points, DeepAutoQSAR performs really well. And it's also optimized to work on GPUs, so it's much faster to get to scan through multiple hyperparameters, much faster to try out all these different algorithms and come up with the best performing one. So with all these deep learning approaches, it's really important to select the right architecture and also do the hyperparameter optimization to come up with the most optimal architecture and hyperparameter combination for that particular model. So all that is completely automated within DeepAutoQSAR, and the hyperparameter search and the architecture search is done automatically using Bayesian optimization. So once DeepAutoQSAR trains a bunch of models, it will take the top 5 performing models and provide an uncertainty prediction based on the standard deviation across the five models. So these are on the right side. You see here some of the models that we've implemented within DeepAutoQSAR. So one example I would like to show where we have contrasted AutoQSAR and DeepAutoQSAR is this particular example of applying machine learning for the design of Redox flow batteries. So this data set was obtained from this paper shown on the left side on the bottom here. And the data set consisted of 1,400 homobenzylic ethers and their corresponding oxidation potentials. So we provided this data set to inside Maestro, our desktop software, and we trained models using both AutoQSAR as well as DeepAutoQSAR. And AutoQSAR performs reasonably well. The R-square, the coefficient of determination, was around 0.94. So the closer this number is to 1, the more performing the model is. whereas DeepAutoQSAR performs even better with a test R-square of 0.98. So this is the coefficient of determination on the molecules that the model has not seen yet. It's a holdout set. So this really shows how powerful these models are. The reason why DeepAutoQSAR performs better here is because we have a larger data set and we can take advantage of architectures like neural network architectures. So in addition to just using 2D descriptors and graph convolutional approaches that I mentioned earlier for AutoQSAR and DeepAutoQSAR, we have a variety of featurization techniques that are very unique to our platform. For example, we can generate DFT descriptors for molecules using Jaguar or quantum mechanical solutions. And we can generate semi-empirical descriptors, which are much faster to generate. And we can generate descriptors that are specific to organometallic systems that take into account the metal center and things like the buried volume, for example. And we also have descriptors for periodic solids. For example, these element descriptors and oxidation state descriptors are actually based on the Matt-Minor descriptor approach, where we take the stoichiometry of an inorganic solid and calculate the stoichiometric descriptors. And we also have a 3D descriptor approach called the smooth overlap of atomic positions, where we would take a molecule or periodic solid, and using the smooth overlap of atomic positions method, which generates a rotationally and translationally invariant basis set for the atomic environments, we can actually characterize the 3D structures of these molecules and periodic systems. And once these descriptors are generated, we can actually add them as additional descriptors to AutoQSAR or to DeepAutoQSAR to improve the performance of the model. And similarly, we have a panel which can also generate polymer fingerprints and polymer descriptors to improve the performance of machine learning models that are specific to polymers. So a concrete example of polymer descriptors is shown in this example here, where we took a data set of around 315 polymers from the Pisarano Polymer Handbook. So we made machine learning models using AutoQSAR without providing any additional descriptor. So basically treating the polymer repeat unit as just a molecule. So when we did this, we got an RMSE of around 38 Kelvin for the root mean square error of around 38 Kelvin for the glass transition temperature. But once we provide polymer descriptors, for example, the topological torsion fingerprints, so the topological torsion fingerprints are a combination of substructure fingerprints that we normalize with respect to the polymer repeat unit, so that just because you make the polymer repeat unit longer, it shouldn't change the fingerprint, because we are talking about large molecular weight polymers. So the topological torsion fingerprints are normalized with respect to the polymer repeat unit. And we also add additional descriptors like the length of the side chain and the number of ring atoms, fused ring atoms, which influence the stiffness of the polymer chain. So if your polymer chain is really stiff because it has a lot of fused rings in the parent backbone, the TG is going to go up. So we can actually construct those descriptors and add those descriptors to improve the model. And we can see here the RMSEs are around 11 Kelvin to predict the properties of these polymers. Similarly, moving on from polymers, I would like to give an example of how we can use a combination of machine learning, of MD, molecular dynamics, and machine learning to improve the prediction properties of molecules as well. So here is a case study where we actually performed machine learning for viscosity, and we carefully extracted more than 4,400 viscosities from the literature. We searched through the entire literature and looked at handbooks, looked at publications, and we filtered out molecules that were not appropriate for machine learning, if they were charged or if they were mixtures, and we removed values which had extreme values of temperature and viscosity. And the goal here was to predict the viscosity at any given temperature of any molecule at any given temperature. So at the end of the day, we had a data set of around more than 1,000 molecules, unique chemistries. And this is the chemical space of these molecules. And the viscosity of these molecules range from 0.1 to around 27 centipoise. And the temperature ranges from around 227 to 404 Kelvin. So these are the distributions of the logarithm of the viscosity, and this is the distribution of the temperature. And this was an overall data set that we had. And the goal was to combine do machine learning in two different approaches. One is the descriptor-based approach, where we generate, for example, RD-kit descriptors, the fingerprint, the circular fingerprints, or also known as the Morgan fingerprint. We generate Matt-Minor stoichiometric-based fingerprints and also molecular dynamics-based fingerprint. So I'll go into a bit more detail about the molecular dynamics-based fingerprints of descriptors in the next slide. But these are basically quantities like the heat of vaporization and the free volume that we calculate for the amorphous system of the molecule. And finally, we also looked at graph-based approaches, and which don't involve any explicit descriptor generation. So we combine the molecular dynamics descriptor with all these 2D descriptors, and we also combine the molecular dynamics descriptor with the graph-based approaches. So here you can see on the top left side the snapshot of an MD trajectory that was used to generate the descriptors for methyl acetate. So we have a particular workflow of running of equilibration, running NVT and then NPT followed by NVT, a 20 nanosecond NVT run to get these descriptors. And so the descriptors that we use around 8 MD descriptors. So heat of vaporization, density, the different Hansen solubility parameters, and also the RMSD. So these are the descriptors that we extracted from molecular dynamics. And we use these descriptors in combination with the 2D descriptor. For example, you can see here on the bottom left, we use the light gradient boosting machine algorithm with 2D descriptors. Then we also use the light gradient boosting machine with 2D descriptors and MD descriptors. And we use a graph-based method called edgepool without any descriptors, and we use a graph-based method edgepool with MD descriptors. So what we see is that adding MD descriptors, especially in the low dataset regime, really improves the performance of the model. For example, here you can see a learning curve. The training set size is increasing as you go along the x-axis. So on the left side, we have a low dataset size regime, and on the x-axis, you have the root mean square error. So the error is going, as expected, the error is going down as we increase the dataset size, because we all know that as you increase the dataset size, the machine learning model performance improves. But what is surprising is that in the low dataset regime area, the MD descriptors are actually performing much better than the pure graph-based approach or the pure 2D descriptor approach. And we see that, and most of our customers are really working with low dataset sizes. So coming up with really powerful physics-based descriptors that can help in the low dataset regime is really powerful demonstration here. So this MD-based descriptor panel is going to be coming out soon in the software suite, and it should be available to generate MD descriptors for any chemical space, and even for molecules as well as for mixtures. So we also did a feature analysis to see which are the most important descriptors for viscosity, and we did this using the Shapley feature analysis, and we were able to show that the heat of vaporization and the temperature were the two most important descriptors for viscosity. So this really shows again the power of MD descriptors for properties such as viscosity. So another example of where we combined physics-based approaches and machine learning is on the optoelectronic properties of chromophores and OLED molecules. So this particular case study was based on a data set that was published in a few years ago, and this data set consists of 20,000 chromophore plus solvents. So 7,000 different chromophores, and their optical properties were measured in different solvents, in 365 different solvents. So these authors actually combined the chromophores and solvents using a graph-based approach, and they were able to obtain a pretty good machine learning model performance for a variety of different optical properties, such as the absorption wavelength, the fluorescence wavelength, the quantum yield, the absorption bandwidth, the fluorescence bandwidth, the fluorescence lifetime, and the extinction coefficient. And this shows the distribution of different solvents that were used for the chromophores. So we also wanted to tackle this data set and come up with our own solutions. What we did was we calculated the 2D descriptors for the chromophore and the 2D descriptors for the solvent, and we concatenated the two. And in addition to that, we also generated DFT descriptors for the different chromophores. So what we noticed was that this approach of using a neural network by combining the 2D descriptors for solvent and chromophore, it seemed to outperform the performance of the model reported by in literature. So Deep4Chem is the model performance that was reported in literature. The MATSI ML is our internal Schrödinger model, which is based on the concatenation of the solvent and the chromophore descriptor. And the MATSI ML DFT is our Schrödinger model, which combines DFT descriptors of those chromophores. And we see clearly, for example, in the wavelength of absorption, combining DFT descriptors definitely improves the performance of these models. And again, we're going to have these features available in the suite for people to make real-time predictions of these chromophores in different solvents. And what we see here, so these are the 20 different DFT descriptors that we generated using our software solution. So using our Maestro software solution, all these descriptors are the workflow for generating these descriptors is completely automated. The geometry optimization and the excited state properties, all these are completely automated, so that it's completely abstracted away from the user. And once you generate the descriptors, we can actually see which are the most important descriptors for these optical properties. For example, for the lambda max absorption, the most important property was a scale gap and the lambda max absorption calculated using DFT, which is not surprising. Similarly, for lambda max emission, the scale gap was also an important property for the lambda max emission. So this shows you the power of combining DFT descriptors for the optical properties of chromophores and OLED molecules as well. So in this particular data set, there were not just chromophores, there were some TADF molecules, thermally activated delayed fluorescence molecules as well. And we plan to increase the chemical space of this data set to include more complex and OLED molecules to make this model more relevant for organic LED chemistry. So moving on to the next scientific case study here. I'd like to showcase how we made a machine learning model for the volatility of organic molecules. So the volatility is actually a property that's quite difficult to calculate using physics-based approaches. And this particular project was motivated by calculating the volatility for ALD and CVD precursors. We have some solutions in our software suite for calculating reactivity and things like that, but not volatility. So machine learning can really fill in the gap in areas where physics-based platform cannot calculate certain properties. So we again calculated we collected a data set of more than 12,000 experimental measurements at different pressures and temperature for the volatility of a huge array of organic molecules. We had more than 1,184 organic molecules in this data set, and there were 12,000 data points because they were measured at different pressures and temperatures. And the pressures were ranging from 1 torr to 30 atmosphere. So it really ranges in a huge range in pressure. And there were 200 chemical descriptors and 1,000 Morgan fingerprints used in these machine learning models. And in order to predict the boiling point, we provided the logarithm of pressure as an additional descriptor. And instead of predicting the boiling point directly, what we do is we predict the inverse of the boiling point, that is 1 by temperature, the inverse of temperature. And the reason is that we know that according to the Clausius-Clapeyron rule, there is an inverse relationship between the logarithm of pressure and the inverse of temperature. So we are making it essentially easier for the neural network to learn these functional physics-based relationships between the property and the descriptor. So we train a wide variety of algorithms to predict the 1 over temperature as a function of pressure and chemical descriptors. And for example, light gradient boosting machine has a root mean square error of around plus or minus 8 degrees Celsius. But our multi-layer perceptron was extremely accurate in predicting the boiling point, and the error was around plus or minus 2 degrees Celsius. And these two gray areas show some other data sets available in literature and some other publications. And from what we observe, this is really the best performing model for boiling point for such a huge chemical space that exists in literature. And this shows you the performance of this machine learning model for four extremely different types of molecules that were not included in the training set. So here we have the logarithm of pressure on the y-axis and the inverse of temperature on the x-axis, and the dots actually show the experimental data points, and the dashed lines show you the machine learning predictions. So what we see is that the machine learning is able to smoothly interpolate across the different experimental data points, and it's able to predict very well these experimental values, even though they were not part of the training set. And it is able to extrapolate to higher temperatures as well. So this really shows you the power of selecting the right architecture and the right descriptors for training machine learning models for these properties. So we have two machine learning models for volatility. One of them is for organic molecules. The other one is for organometallic molecules. So when we take those two models into consideration, The applications can range from atomic layer deposition and chemical vapor deposition to thermal evaporation and jet printing, flavors and fragrances, and a variety of different applications for these two models. Finally, moving on from molecules and organic systems, I'd like to give a quick case study on machine learning for inorganic 3D crystals as well. So in this particular scientific case study, we actually download a data set that's publicly available. This data set is from the Nomad 2018 Kaggle Challenge. So this was 3,000 periodic structures containing indium, aluminum, gallium, and oxygen. And what we wanted to try was to make a machine learning model to predict the band gap of these different 3D structures, which we downloaded as CIF files from the website. And we provided these 3,000 structures into Maestro and loaded up the DeepAutoQSAR panel. And we generated both the composition-based descriptors. The top three here are the composition-based MapMiner descriptors. And we also generated 3D SOAP-based descriptors to see which ones perform the best. So these are how the crystal structures look like within our Maestro software solution. And this shows the machine learning performance using DeepAutoQSAR. On the left side, we see using just 139 MapMiner composition-based descriptor, and on the right side, we see the MapMiner descriptors plus the SOAP descriptors. So the SOAP descriptors are a basis set representation for 3D atomic environments, and they're extremely sparse. The dimensionality is very big. So we need to reduce the dimensionality using things like principal component analysis. So we brought down the dimensionality to around 10 descriptors using principal component analysis. So by combining these two sets of descriptors, we can get a really good performance that can predict the band gap of these transparent conductive oxides with a pretty high level of accuracy. So I've given you guys a huge number of case studies that we've performed. So we are performing these case studies to help us validate the different products that we want to implement for our customers. And one product that we have is called the Machine Learning Property Prediction Panel. So this product is already available within the Schrödinger software suite, and it is a panel which can make predictions based on models that we have trained within Schrödinger suite based on our own proprietary data sets that we've collected from literature. For example, we can predict the boiling point and vapor pressure of organic molecules, of organometallic molecules. And as I showed earlier, we can predict the glass transition temperature of any homopolymer. And similarly, we can predict the frequency dependent dielectric constant and dielectric loss of homopolymers as well. And finally, we also have machine learning models that can predict density and viscosity of molecules. So these models are already available within the Schrödinger suite, and we plan to continue to adding more and more properties to make these machine learning models more user-friendly and more useful to our customers. So these are all models for different things like polymers, molecules, and solid-state materials, but sometimes we are dealing with the mixtures of molecule. And in that case, we really like to do machine learning for formulations. So we are currently working on a machine learning for formulation panel, which can take a CSV file where you have different materials, different molecules, but you would have maybe like 20% of one molecule, 30% of another molecule, and 50% of another molecule. You will load that CSV file into the formulation machine learning panel. And the formulation machine, and this is a quick snapshot of how this panel looks like right now. You would have the different molecules with the smile strings with a different composition, and you have different properties. In this case, we're actually looking at properties like these are heat of vaporization and density that we've generated based on internal formulation data sets that we've acquired. And the machine learning model would automatically generate descriptors for each of the molecules present in the data set. It would do a weighted average and standard deviation and maximum and minimum of all the descriptors, and it would concatenate all these statistical quantities for these different molecules based on their relative composition. And it would try out different types of machine learning algorithms like XGBoost or multi-layer perceptron, and it would come up with the best performing model that was optimal for that particular formulation. And going forward, we will be providing solutions to provide Shapley feature analysis to come up with what are the most important ingredients for a particular property and what are the most important descriptors that affect a particular property as well. And as you can see, DeepAutoQSAR gives a standard deviation and uncertainty as well. And with the help of this uncertainty and prediction and the actual prediction value, we can actually use active learning and sequential learning to come up with new chemistries. So this is a very automated solution to basically train machine learning model for mixtures, for example, for battery electrolytes, and come up with new mixtures and new formulations. And and use a machine learning model to make predictions on the new formulations to validate before you actually go ahead and synthesize it. So once we have machine learning models trained for a particular property, we want to use it to come up with new ideas, new materials. And this is where things like active learning and genetic optimization are really powerful. So in active learning, for example, we have a completely automated solution for active learning for OLED molecules for optoelectronic properties, where the user may want to try to, for example, maximize oxidation potential, minimize reduction potential, and choose a particular value for a triplet energy. And the user can choose his multiple criteria using this panel and run DFT. But instead of running DFT for example, 10,000 compounds or 1,000,000 compounds, what you would do is enumerate all those 1,000,000 compounds and provide it to Maestro, and Maestro would start with just 50 random DFT calculations, and it would automatically select the next best calculations. For example, the next best 10 molecules to perform, which are most closest to the property of interest based on your multi-parameter optimization score. So using this, so all you need to do for active learning is to provide a enumerated list of compounds, and this and the computation with DFT, the selection with machine learning, and then adding the DFT, the newly trained DFT molecules back into the training set, and training the machine learning model again. So this cycle is completely automated, and we have some publications showing how this can be used for designing new OLED molecules, for example. So in active learning, we need to provide the large pool of candidate molecules. But what if you want to completely start from scratch and you just want to come up with new ideas? This is where genetic optimization can be helpful. So we have an optoelectronics genetic optimization panel where you don't need to provide any enumeration. All you need to do is provide some parent compounds and a library of substructures of R groups. So what did it do? It is automatically, so this in the genetic optimization, we can use DFT, and we can also use a machine learning model. For example, in this case, I trained a machine learning model to predict the delta EST value of a OLED, TADF OLED molecules. And the goal here is to make predictions or to come up with new molecules which have a delta EST value of close to the 0. And we want to minimize the delta EST value here. And once we've trained a model with AutoQSAR, we can provide the AutoQSAR model to the genetic optimization panel, and we can ask it to minimize this property based on random mutations and by combining different substructures in the parent structures. So, we can add DFT properties, and we can also add machine learning properties, and we can, again, similar to active learning, we can construct a multi-parameter optimization scheme which will allow us to simultaneously optimize multiple properties at the same time, and the chemistry will be mutated and randomly selected so as to optimize those particular properties. So here I was able to, the red histogram shows the distribution of the training molecules for the delta EST values. And after 5 generations of the genetic optimization, I was able to generate a huge number of molecules which had a particular delta EST value of close to 0. And you can also put in additional constraints like molecular weight constraints and other constraints to increase the efficiency of genetic optimization. So finally, I'd like to talk a bit about machine learning force fields. Initially, until now, we've been talking about how we've used machine learning for property predictions, but there's a more direct way of combining machine learning and physics-based simulations, and that is through machine learning force fields. So in machine learning force fields, you actually the goal is to come up with a force field that is as accurate as DFT, but at the computational expense of close to OPLS or close to an empirical force field. So in order to do this, we need to generate a huge data set, millions and millions of compounds and different conformers, and look at the energies and forces of these molecules. And we used our first approach for coming up with a machine learning force field was called the Schrödinger ANI or SANI force field. And this supported around 8 elements and had a coverage of 94% of drug-like molecules. And in Schrödinger ANI, each element has a separate neural network mapping from the atomic environment vector to the energy. So in Schrödinger ANI, we trained to both energies and forces, but we didn't include any long-range effects like the Coulomb interaction or electrostatic interaction. So These effects are what we considered in our next generation of machine learning force field, which we call QRNN. These are charged recursive neural network force fields, which is really it's a fourth generation type of machine learning force fields, which are trained not just to energies, but also to energies, forces, and dipole moment, for example. And here the neural network would automatically predict the charges of on each atom, because we include charge-dependent atomic environment vectors to learn the radial charge distribution. And once we have the charges for these of every atomic site, we can actually calculate the empirical dispersion correction and Coulomb correction and add these corrections to the total energy. So these models are actually very accurate, not just accurate, they span over a huge chemical space, and they can calculate properties of charged molecules as well. That shows the power of it. So these machine learning force fields have really come a long way in becoming more accessible and more useful for a wider range of applications. For example, one clear example of using this machine learning force fields is for battery electrolytes. For example, here we created we looked at the properties of electrolytes such as ethylene carbonate, propylene carbonate, and we calculated the properties using QRNN and using OPLS4 and compared it with experiments. And the light blue bar charts show the QRNN, and the gray bar charts show the experiment values. And we see for certain properties like the diffusivity and the viscosity, we see a very good agreement of QRNN with experiments and a significant improvement over OPLS. So we really see the potential of these machine learning force fields for a wide variety of applications. And once you have a machine learning force field, for example, you can look at a formulation of ethylene carbonate and propylene carbonate. So you're not limited to a single molecule prediction. The physics are much more universal and can be applied to a wider variety of applications. So this force field is going to be available in an upcoming suite, and eventually we are planning to deploy an automated training protocol which will help our users to automatically generate a machine learning force field for the chemistry of interest. Finally, I'd like to conclude this talk by talking about our enterprise informatics solution called LiveDesign. So LiveDesign actually brings everything that I've been talking about previously into a single platform. If you have experimental data, computational modeling, and data analysis and machine learning, and if you want to have access to all of this in a single browser-based collaborative platform, LiveDesign is the best solution for this. So, for example, experimentalists can run assays and upload their dataset to a live report, and a machine learning expert can train models and deploy those machine learning models to the experimentalists for them to use. A computational chemist can deploy DFT and MD workflows within LiveDesign as well. So it really brings together all these different three important areas to help a company come up with new chemistry and new formulations and new ideas. So we've extended LiveDesign to work beyond for just small molecules. Now it works for molecules, polymers, organometallics, and experimental data as well. And we can come up with customized gadgets. So every company has a particular format of formulations or the way they represent the data, and we can come up with customized JavaScript gadgets basically that can be tailor-made to the format required by a customer. With that, I'd like to summarize my talk. During this talk, we realized how important a customized featurization approach is important to generate machine learning models for material science and chemistry. And in addition to customized featurization, we use physics-based approaches to either to generate a high throughput data set or to generate descriptors like MD descriptors or DFT descriptors that can really make the machine learning models more generalizable and more accurate, especially when you have low data set sizes. And we've demonstrated our machine learning capabilities across a broad range of applications, ranging from polymers to optoelectronics and to solid-state systems. And all these models can be brought together into LiveDesign to enable things like a sequential learning, formulation machine learning, and analysis and visualization. And finally, another very crucial way of combining machine learning with physics-based simulation is machine learning force fields, which are very generalizable and have the accuracy of DFT level accuracy, but are much more computationally tractable and much more computationally inexpensive. So with these different approaches, we think Schrödinger is well suited to tackle machine learning for material science and chemistry by combining physics-based simulations and chemistry-aware machine learning. So with that, I'd be happy to take any questions, and please feel free to reach out to me if you have any additional questions as well.
Thank you, and there's an awful lot in that presentation, but then it's a system with so much potential that there's so much to talk about. And we've also had an awful lot of really good audience questions. There is still time to get your questions in. If there was anything that was just in the back of your mind, now's the time to type it in. We have just shy of 15 minutes. We'll get through as many as we can. So let's kick off with Jay. Jay asked, in polymers, the processing conditions also really matter to determine the properties, for example, the extent of crystallinity. Should that, or is that part of the features of this platform?
That's a very interesting question. So the processing conditions are important. For example, the frequency-dependent dielectric constant of polymers, the frequency is an important property, important measurement parameter to predict the properties of the dielectric properties. So the user can input the frequency as an additional descriptor to predict the properties of the polymer at different frequencies. So the user can also input like things like temperature and pressure, and for example, if you have any additives, those additives can be converted to additional descriptors and put into AutoQSAR. So the processing parameter can be added into AutoQSAR to take that into account. So it's not explicitly available as a descriptor. For example, we don't have a descriptor to take into account specifically for cross-linking or for copolymers, but it can be done in a more indirect way. And certain things like degree of crystallinity, we have, for example, a semi-crystalline polymer builder where you can actually build a semi-crystalline system with different degrees of crystallinity. So those may be a better approach. There might be a physics-based solution. Yeah.
Fantastic, thank you, Jay. It sounds like already something you've clearly thought about. Thomas asked, are there any specific, or is there a specific data bank for data sets of molecules of interest, such as fullerenes and dyes for solar cells?
So in terms of fullerenes, I am not aware of any data set myself. In terms of dyes for solar cells, the chromophore data set could be a potential data set that could be relevant to you. As such, Schrödinger, we don't really focus on, as we focus on data set generation internally so that we can make machine learning models available. As of now, we don't really, the data set is not exposed. So we don't really offer any solutions to data curation and supplying data to customers at the moment. That could be something we could look into the future, but as of now, we don't have any solutions for data sets. Yeah.
Schrödinger have a lot of academic partners. You work with a great deal of researchers and so on. Is that what drives your decisions as to what data sets you want to generate, even if they're not exposed to the end user? Is it the academic research in the background that's telling you, oh, this is definitely a data set that we should have our hands on?
Yeah, definitely. That's exactly what we do. I mean, we are extremely motivated we're extremely motivated and grateful for the academic community for their work. For example, the chromophore dataset for organic molecules was from literature, and the viscosity dataset that we've published, based on the MD descriptors, we've done the entire case study. We've written a publication, and the dataset, most of the dataset is actually shared along with the publication as well. So we hope to give back to the academic community as well through that as well. So once we get it published, we'd be happy to share the dataset. Yeah. Yeah. Super.
Nice to hear that it's able to come full circle in that way. Henry asked, with DeepAutoQSAR, what is the maximum size of molecules? And part two for Henry's question, can it be used to model 2D materials at a smaller or larger scale?
Oh, the maximum size, there's really low limit to we've done huge molecular weight compound. OLED organic LED molecules are pretty large molecular weight systems, and we've had no problems using those for DeepAutoQSAR. And in terms of the data set size, the molecule size, the molecules can be huge. There's no issue. And in terms of data set size limit, I've heard customers using our data set on 50,000 molecules, training a model for 50,000 molecules using DeepAutoQSAR. And for AutoQSAR itself, the limit is around 5,000 molecules, but for DeepAutoQSAR, it can be huge. Yeah.
I think we saw some of this in your presentation anyway, where we saw the charts comparing measured to the predicted results. But Eddie has asked, have you found a high degree of agreeableness between machine-based outputs and your experimental findings?
So we don't do experiments ourselves within Schrödinger, but we always validate against experiments. So especially like the advantage of machine learning is that you can directly train machine learning models on experiments, and that's a beautiful part of it. So all the chromophore data sets for the optoelectronic properties, the optical properties, the absorption wavelength, all that was experimental properties. The viscosity was also an experimentally measured experimental property. The glass transition temperature was an experimentally measured glass transition temperature of polymer. So we do see a very good agreement between machine learning and experiments. Of course, with machine learning, we have to be careful about extrapolation. But like we have to be careful when you try to extrapolate to a different chemical space or a completely different property space. But in general, we do see a pretty good agreement between machine learning and experiments. And that's the advantage of machine learning, that we can train models on properties that we can't generate with physics-based solutions.
Thank you, Eddie. Great question. And with that in mind as well, do Schrödinger's machine learning tools give you like an uncertainty estimate when you are extrapolating from existing data? Does the model tell you this is my estimate and this is my confidence in it?
Yes, it does. I mean, but right now the uncertainty estimate is based on the standard deviation. So both AutoQSAR and DeepAutoQSAR use an ensemble of models. So you can see uncertainty. You can once you make a prediction, you can get both the prediction as well as the uncertainty. And if the uncertainty is huge, then of course one should be very careful about training a new model. And the uncertainty estimates are also used, for example, in active learning. So when you're trying to do active learning to select the next best molecule for doing DFT on, we're not just trying to optimize like especially when you have a small data set size, you don't want to get stuck in a small minima, like a small chemical space. You want to explore as much as chemical space as possible. So we use a combination of uncertainty and the prediction. We use something called the expected improvement function, which can tell you I want to go to some place uncertain specifically, get that data set and do DFT and do machine learning on it. So yes, uncertainty is important, and it's definitely still an ongoing field of research, and we are paying attention to what's going on in literature. Yeah.
Super. We have a question from Romain, who not only says hello from Finland, but also wants to thank you for sharing really interesting results. Romain asked, why, while an important data set is yielding good machine learning results, how do you know all of your data are useful or relevant to your model?
That's an interesting question. So we are careful in curating. Well, in terms of we can look at our uncertainty. For example, if you train a bunch of molecules for viscosity, and we see that a lot of molecules contain silicon, and those silicon-containing molecules may not potentially be of interest to customers, we would remove those molecules. And we usually do an analysis based on the chemical space, or we look at outliers based on the Tanimoto similarity, or we look, yeah. So it depends from case to case, but it's done manually. We have to curate the data. I mean, the data set curation is the most painful part of machine learning, and even that I'd say 70% of the time is going in curating the data set and removing outliers and removing points that could be problematic. And that's still a manual process. There's no way to do it automatically.
We have 5 minutes left and still lots of great questions coming in. Clearly your email address is on screen now, so if people want to email you, it's very kind of you to make that public. People can follow up with you. But also we're going to send all of these questions on to Schrödinger, so that it may be that if there's something people can get back to you about, then they will follow up on that. So even if we do run out of time and I don't get to your question, that's not the end of it. But thank you so much for all these great questions. Let's go for Mutakuma has said, are the machine learning parameters available for polymer property predictions for charged polymer systems?
Unfortunately, no. For charged polymer systems, it's not available. And I presume, like, if, for example, if you're looking at I don't know, polymer ultralight, maybe you're interested in charged polymer system, or as of now, we don't have any solutions for charged polymer systems. We could use QRNN to make predictions on, or to do simulations on a charged polymer system with an electrolyte, with a cation or an anion, for example, and those could be handled with our machine learning force field, but not necessarily with our. Right now, we don't have any solutions for the property prediction. So if you have a data set with charged polymer systems, and you could add the charge as an additional descriptor and try to make a machine learning model, and that could be a potential workaround. But we don't have any current models. We haven't tested it yet.
Super. Thank you for the question. Let's have a look. We might get two more in, I think. Wythe says, thank you for the nice talk. For TCO, not only is knowing the band gap important, but also potential defects. So have you dealt with, or can you predict any useful dopants by using machine learning methods?
Oh, that's a very interesting question. So as of now, we have not tried looking at defects and defect formation energies, or how defects affect the band gap and optical properties for these systems. But we are looking at more featurization techniques like magnet or other approaches where you have a machine learning model trained on like hundreds and thousands of solid state systems, so you can actually predict machine learning properties for these systems with defects. Right now, we don't have any machine learning based solutions for that. And we do have a quantum espresso. We have a graphical user interface for quantum espresso within our Schrödinger solution. So using, again, physics-based solutions to calculate the defect formation energies, or calculating the band gap and the density of states, and with quantum espresso, a GUI, that could be the best way forward. Yeah.
Super. Thank you very much for your question. I think that probably is all we're going to fit in, but as I said, we'll send all of these on, and details are on screen now if you'd like to follow up. And thank you so much. As I said, there's an awful lot that you've packed into the last 45 minutes or so, and it was fascinating stuff, really interesting one to follow up. I hope that we will hear from you again soon. I look forward to seeing how this develops. A system with so much potential, and I can really see how our community will pick it up and run with it, and I'm sure that it will be developed very rapidly and continue to give fantastic results. So Anand, thank you for your time. Thank you to Schrödinger as well. Obviously, Anand represents Schrödinger here, but as a broader company, there's somebody that we work with at Chemistry World quite frequently, because they serve our community very well and they're doing some very interesting things. Always happy to have them in as a partner, so thank you for that. And thank you to all of you for asking so many fantastic questions that really were far more than we could get through, but as I said, we'll send them all on. We'll do our best to get answers to as many of you as we possibly can. Go to chemistryworld.com/webinars to find out about all of our upcoming events, or of course chemistryworld.com for all of the latest news, views, research and opinion from across the chemical sciences. While you're there, you can make a free Chemistry World account that allows you to read far more. It also gives you access to things like our reaction newsletter, which is a curated roundup of news from a range of different sources that cover the full breadth of chemical sciences and will land in your inbox every week. Once again, thank you to Anand for joining us and delivering such an excellent presentation today. I'm Ben Valsler, Chemistry World's digital editor, and I will see you in the next Chemistry World webinar. Thanks again.